Okay, so tomorrow will be your last test, programming test number 3. My last minute tip would be you want to definitely try to see if you can redo lab number 4. Yeah, if you see if you can redo lab number 4, and also lab number 2 will be useful as well. And if you really have time left, you can also give a try on the previous practice test, especially practice test number 2 about the different stuff that we kind of guide you through. It'll be very useful. And apart from that, your programming test number 2, the result and feedback have been released. If you got any questions, you can talk to me during office hour. If you want to submit a regrading request, just make sure to submit it in time. So lab number 5. So this will be the final lab. I kind of released that late. It's not your problem. So in that case, I still keep the deadline as originally planned, like December 2nd, which will be next Tuesday. However, if you want to take more time to work on your own solution, no problem. You can take 1 more week. It will be until December 9th, midnight. Okay? You can still submit by December 9th without any penalty. It will still be okay. And right after this grace period, I will release the solution to that. And just notice that for this particular lab, number 5, there will be some required background study you have to make sure you do on your own. So it will be on abstract classes and interfaces. But given how much in depth we actually talk about inheritance, studying for these 2 subjects should not be a problem. So I gave you the lecture recording, I gave you the slides, and also all the notes. You can choose whichever medium you would prefer to actually study for these 2 topics. They are important, but it's more like a natural extension to what we discussed about inheritance. Make sure you study for these 2. They will be part of the coverage for exam. Yes, question? Do you know the abstract stuff for the test tomorrow? No, definitely not. Yeah, so for tomorrow, your programming test number 3, as I said in the guide, is only lab number 4, mainly. Yeah, but it says also lab number 2, I would say just review the basic OOP stuff. And exception could be useful, just kind of brush up a little bit. Doesn't mean we'll put question on that, but just get prepared.
And yeah. For the, like, let's say there's a questions, if it says like explicitly, what's it called, like there's an exception, we do it. But if it doesn't have the exception, like explicitly stated, we don't have to.
Exactly, yeah. Normally, I think we'll give you the explicit hint about using the method called some try and catch block. If you do see that, that means you got to put some exception, right? Okay, good. All right, questions? Okay, so I would suggest today we skip the recap just for inheritance. We are done, completely done with it. So please start going over your the material about inheritance. They will be definitely covering the exam. Okay, there are quite a bit of stuff we spoke about, which were not really covered in your written test number 2. Oh, the written test number 2, I already coordinated with the TA. They're now busy grading the written questions. I'm hoping to get back to you, let's say by the end of Friday, if not earlier. Okay, I will see the TA again tomorrow. Hopefully they will bring me some progress. I'll keep you posted, but Friday should be okay. Only 1 question to be graded. Okay, all right. If no question, I would suggest we start fresh about recursion, right? So as I said, I don't assume any prior knowledge about recursion. So we only need about 3 lectures to really cover what I think would be the basic just at this level for this course. But when you get to 2101, next term, it doesn't really matter which instructor you might be taking with, but I think recursion will be definitely done again, in a different context, I would say. But, it depends. If you take it with me again, you'll definitely learn a little bit more in-depth knowledge about recursion next term, but not for this term, okay? So as I said earlier, let me just remind you very quickly. So all the study resources for recursion have been made available to you, all right, right here. So you can see that section there about recursion, okay? Right here, you got notes, you got slides, you got example code, everything is there. So I would suggest just start navigating the resources about recursion. If there's anything you have in doubts about these resources, just reach out to me. I can give you some guidance. But these are more than enough what you will need for the exam. Okay, just make sure you study through the exercises. Don't memorize them. That's not the way to go. Make sure you study the principle. That's something I will emphasize in the lectures. Okay. So the plan for today, I want to talk about recursion, just the principle about programming in recursion. We're thinking recursively in general, and then we'll do the so-called hello world example to recursion, like Fibonacci and also factorial. We do these 2 just for today. And then I will cover some important string methods that you might need actually whenever you program recursion on strings. There's some certain method I want to clarify, and we might just do 1 recursion problem on the string. And then on Thursday, when we come back, we're going to do more examples. And then also next Tuesday will be the last class. We'll do more. All right? Okay. And it's very likely that if you look at the recursion slides, towards the end, there is one example called Tower of Hanoi. It's a very interesting example to really train your recursive thinking. It's definitely got to be covered in the exam. However, we may not be able to talk about everything about the example. I'll try to give you some highlights at least, maybe next Thursday. Oh, next Tuesday, I beg your pardon. We don't have any more classes on Thursday, too bad. Okay. So next Tuesday, I'll give you some very quick highlights if we cannot talk about everything about the Tower of Hanoi. But I do have some nice lecture recording for you to go through. You definitely have time before the exam. Okay, excuse me. All right, let's now talk about recursion. So we're going to talk about how to solve problems recursively. So there is some very simple pattern of the principle we can simply go through. Just a few bullet points to really get through. But the same principle can just be applied to all the recursion problems in general. Doesn't matter how complicated it might be, just a recursion. Okay. And then we talk about recursion on strings and also recursion on arrays. So these are the two types of problem you can expect on the exam, either on the string or on the arrays. We'll do string today, and also maybe at least the first half on Thursday. And then we'll talk about how you can do recursions on the array. And we have to revisit call by value again to see how things can be done efficiently, especially if you want to have recursive calls on the arrays. And the Tower of Hanoi, if we have time, I would love to talk about more details about Tower of Hanoi. If no, I'll at least give you some highlights about which part you want to pay more attention to. Okay, that example there. All right, and then just want to give you some very quick reminder. If you want to do extra practice, you can also go to the coding bat, especially recursion 1. I think that one there has many good examples for you to try it out, right? They got one of them. So if you try maybe one each day until the exam, you can finish them all, right? Just plan some study rather than going through everything in 1 or 2 days. May not be the way to go. And this will be beyond the scope for this course. Usually when students ask me what will be my advice on mastering recursion, I would say in general, we got very limited time for each course to really give you some very thorough experience about recursion. So I would say you really want to maybe dedicate your time, maybe after the class, beyond every class, to really do something more serious. One thing I would suggest is to learn about the so-called functional programming language, where you cannot get away from using recursion to program many things. So Haskell is actually one of the very popular or mainstream functional programming language. You can definitely give a try on that, but of course, this is not covered in the exam, right? I'm just suggesting if you really want to get serious about recursion, which is a very important technique anyway, okay? You can definitely go for that. And if you take a 2101 with me, for example, in next term, I'll give you maybe another advice about how you can do sharpen your skills for recursion, but not just yet for that tip, okay? All right, let's now get down to principle for recursion, okay? Let's go over just a few bullet points, just go over the principle, and then we'll visualize the principle, and then we do examples. Recursion is a way of thinking. So recursion is usually compared against iterations, like using a loop. So there are certain problems it will be more convenient to solve using loops. There will also be some problems that will be much more convenient solving using recursion. So you have to make a selection. But for this course, in the exam, we will tell you explicitly whether a particular problem should be solved using a loop or using a recursion. We'll tell you explicitly. You don't really have to make that judgment. But as you get more and more experience designing algorithm, programming your own classes, you will have a very good instinct about which one to use. But anyway, recursion is a very good way to think about solutions and also problems that can be thought of recursively. We'll see example. So there are two phases to design the solution for your recursion problem. So the first phase will be base cases. Think about base cases are the very small inputs which you can compute a solution right away. You don't really have to go through any recursive step. You can just calculate, for example, what's the factorial of 1? Just 1, just return 1. You don't have to do any further computation. But if I say, what's the factorial of 100? In that case, you may have to take more time to actually compute a solution. So base cases are simply just small enough inputs that you can calculate the solution right away. Base cases. You want to make sure you always start with the base cases to get some feel. The second phase is called recursive cases. Anything that's larger than base cases input, you have to call them recursive cases. Okay? We'll get to more details about it, but they are simply larger problems. They cannot be solved immediately. You have to somehow divide the original big problem into strictly smaller problems and then try to get solution from them and then combine the solution together. Okay? That's usually the general principle. Okay? You want to solve by reusing solution to a strictly smaller problem. Okay? So we'll talk about this one here when we visualize it. Okay? And this bullet point is like optional. So for those of you who might be more having mathematical mind, you may want to compare the recursive approach with mathematical induction. Very similar. In mathematical induction, we also got base cases and also inductive step. That's exactly kind of the two phases we have for solving problems recursively. All right? Let's now visualize this pattern. You can see the pattern here itself is very simple, just a few bullet points. That one there is enough for solving problems recursively. All right, let's now visualize very quickly. Okay, we'll start with base case. So this part here, the first row here is the base case. Okay, base case. And sometimes may not be just a single one, could be multiple, right? Usually you will get 1 or 2 or 3 base cases, maybe no more than 3, typically. You're given, so the blue box is the problem, the green box is the solution. Given a problem that's small enough, you can get a solution right away. You don't have to divide it any further. You can get a solution right away, by definition. Okay? You can think about this one basically is computed right away. Computed and return right away. Okay. On the other hand, if you're given some problem that's actually sufficiently big, or anything that's bigger than base cases, okay, you're given something that's big, I cannot solve it right away. In that case, I'm going to divide this problem here into individual pieces. I'm going to do something called divide. I can divide the original problem into subproblems. You can think about subproblem number 1, subproblem number 2, and subproblem number 3. The important thing to remember is each subproblem must be smaller, strictly smaller. They cannot be of the same size as the original problem. It's a very important principle to remember. But we'll show you some cases where, what if you have not strictly smaller problem? What's going to happen? Okay. And now the next step is kind of sounds magical. We assume there are solutions to all the smaller problems. We assume. All right? So we assume that this is the solution number 1 to this subproblem. This is solution number 2 to this subproblem. This is solution number 3 to this subproblems. Programmatically, this particular step simply means I can make some recursive call on the strictly smaller input and assume the correct output is going to be returned back to me. I can assume that. Okay? I'll write it down. Okay? So in Java, or in any programming language, all the programming languages will support recursion to some sort, as long as they support function call or method call. Okay, in Java, you can make recursive call. Recursive call can be a single one or can be multiple ones, and you can assume correct result returned. You can make as many recursive calls as you like, but typically it should be no more than 3 or 5, right? Maybe the one we'll see as example, maybe 1 or 2. That's very typical. Okay, so finally, once you get the correct result returned from each individual recursive call on strictly smaller problems, you cannot combine them somehow, because you cannot simply return all the 3 solutions here as the solution for this big problem. It's not there yet. It's not there yet. You just need one more step. So the final step is something called concurred. You're going to somehow combine all these solutions together, and then that will make a single piece for the original problem. Okay? So that's more like a concurred. Okay? So you can think about this right now. You can think about this particular pair. So that's the original problem. That's too big. And that's the final solution. To really go from here to here, you have to split into strictly smaller problems and try to combine individual solutions. Okay. All right, one final thing, and then we'll do some concrete example. So in Java or in any programming language that can support method call or function call, whenever you see that in the definition of your method or function, okay, here let's say the method is called m. I'm calling m itself somewhere. As soon as you have this kind of self-call, it is recursion. All right? So you can see m is calling itself. Calls itself. So this is so-called a recursive call. Depending on your need from the computation, you can have as many recursive calls as you like. But here's the principle. Let's take this one, for example. Let's say I here is some integer value. If you're trying to make a recursive call, you should put some value there that's strictly less than I, right? It's a bit like, originally, I'm trying to solve the problem for I, but I want to split that into individual problems. In this case, this one here will be just j. That should be strictly smaller. Let me write it down. I'll answer your question. Yeah. So this one here should be j strictly less than I. Yeah, question.
You mentioned when a method calls itself, that's recursion. What if like method m to call method x, and then method x calls method
Yeah, it's a very good question. Yeah. So your fellow student basically was asking, what if, well, first of all, this one here, m calling itself, for sure is recursion. To be more explicit, it's called direct recursion. Okay, I'll write it down. This one is called direct recursion. And what you're saying there is another type of recursion, indirect recursion. It could be that I have maybe n calls n calls back n. It's also possible, but we don't quite discuss in this course. It's also another kind of recursion, in which case you also have to be careful because you want to make sure you don't really circularly actually call the method indefinitely, in which case you might run into trouble. Okay. So in this course, we are focusing on direct recursion. It's a good question. Okay, direct recursion. Any questions so far? All right. So let's now do our very first example. Okay, before that, you will see that on the slides. Okay. So now we are done with slide number 4, and slide number 5 just basically revisit about the points we spoke about. Remember back in the week number 3, we spoke about like a chain of method called caller, callee. We already spoke about stack, right? So that one there, I'm going to assume you guys know about the details. But I can just skim through the slide just to brush up, okay? And then let's do our hello world example number 1, okay? Factorial, okay? So the plan will be, let's talk about just how we can think about this factorial here recursively, and then we'll see how the Java code will look like, and then we'll try to trace it using 2 different methods. There are 2 ways to trace recursion in general. I'll show you both. And then we might just take a short break and do Fibonacci as well. Okay, let's do this one here carefully. Right, factorial, let's say n factorial. If n happen to be 0, is a base case. By definition, it's 1. If n is larger than or equal to 1, in that case, we apply this definition here. However, if you look at this definition, which is completely valid, right? So for example, if you try to do, let's say, I want to calculate 4 factorial. By definition, because it's larger than or equal to 1. So I'm going to do 4 multiply 3 multiply 2 multiply 1, which will be 24. By definition, very simple, all right? Let's clarify. This definition completely valid. However, it's not a recursive definition. Okay. This is not a recursive definition because, especially for this case over here, where the input is larger than the base, you can see in this particular definition here, we are not really trying to call the method itself because we are trying to define what a factorial is. But this factorial sign is never used again in the definition itself. In order to be recursive, it should be reused over here. Okay, let's write it down here. So you can see this definition here. The function being defined. In this case, the factorial is not reused or called over here. Remember what we just said earlier, in order to be a direct recursion, you must call the method itself inside the definition, but we're not doing it, so that's not recursive. All right, so first of all, let's understand why this is not recursive definition, okay? Yeah, of course, the next step would be we want to think about what would be the recursive definition, right? So for that one there, I'm not going to trouble you. It's actually very easy to derive, okay? We'll see. Okay, let's take a look at the recursive definition for that, okay? So let's now look at that. So we're going to do recursive definition. Another thing I will also suggest, because most of you might be learning recursion for the very first time, which is completely fine. You're supposed to learn from scratch. If you're given some programming problem about recursion, I would suggest you always try to sketch about the base case and also recursive case on a piece of paper. Just get some idea before you try coding. Don't really try to start coding recursion right away. I would suggest have a plan first. Okay. So recursive definition. So we say that n factorial, let's now split into, again, base case and recursive case. So you'll be 1 if n is equal to 0. So this obviously is the base case. And in this case, we only got one base case. All right? And recursive case, we say that it's going to be n multiply n minus 1 factorial. All right? If you can say n larger than or equal to 1, or you can say n strictly larger than 0, they're equivalent. Okay? So this one here is the recursive case. It is the recursive case because you can see that the factorial and also factorial, they're the same, right? You can think about this is more like a recursive call. Okay? The function is defined by itself, but on a strictly smaller input. And you can think about if you compare n minus 1 and also n over here, you can see in order to define the factorial for n, we can reuse the definition of factorial of n minus 1, which is strictly smaller. Okay? To define n factorial, we use the definition of n minus 1 factorial. And think about the n minus 1 here is a strictly smaller input. Strictly smaller input. Yeah, factorial is a very simple example. Maybe we're trying to overanalyze what's going on there. But that's a nice little example there. We can see many things, many ingredients there. Okay? Any questions so far? All right. So given this, we can now write a Java code, which is here. All right. So that's a recursive definition we just spoke about. And this guy here is the Java code. Of course, there are different ways you can write it. I kind of write in a way I thought might be nicer for me to kind of visualize. Okay, so it's accessor, integer, and call factorial, and takes an integer input. And then we got some result. Eventually, we got to return the result. Result can be reassigned in two different ways. One is the base case. When n is equal to 0, corresponding to this case, it should be result equal to 1. 1 here. And otherwise, it will be the base case, recursive case, which will be n multiply factorial of n minus 1. You can see the one-to-one correspondence between the recursive definition and also the Java code. All right? Questions about seeing the correspondence? All good? Okay. And let's now try to trace. Okay. So there are different ways to trace the code, recursive method, right? Let me write it down here. So when we talk about tracing, recursive methods, The first approach is something you kind of know already when we talk about how to trace a chain of method call. It's really just a little bit more sophisticated. We will do that today for one example. And then I will also assign one exercise for you, okay? Using a call stack. So pros and cons. Pro would be it really simulates how computer works at runtime precisely. Because whenever you got some method call, you're going to put it onto the stack. When the method call terminates, you're going to remove it from the stack. Right? So that's a very precise way to trace. What about con? The disadvantage about it is you can easily lose the big picture about what that method is supposed to calculate. So whenever you want to somehow get some intuition, whether or not your method is correct, but you program it recursively, using a stack may not be the way to go, especially when problem gets more and more complicated. Okay? For complicated task, using stack can make it difficult, make it hard to gain intuition about the correctness of your recursive method. Okay? But you should know how to do number one. But we'll do that for factorial. It's easy enough for us to see how things will work. The second method is by using we call a recursion tree. Okay? The second method. Using a recursion tree. And for the idea about tree, you don't have to worry too much. You only need to know about how I exemplify how to trace the recursion using a tree. You don't have to understand what a tree really is, because to define a tree precisely, we will have to wait until 2101 to see its formal definition. Right? For this course, just see example. Okay? A recursion tree. And this one here, whatever that used to be pro is now the con. It's not exactly how, you cannot see exactly the call stack, right? Because it's a tree, it's like a higher level. But whatever that used to be the con is not a pro. It's a very nice way to really see how you can, why my method is actually correct using a tree to trace it. All right? Of course, once you get more experience, you might stick to number two a little bit more. Okay? But for this level here, I think we should know both. All right. Let's now take a look at how we can do both over here. And let me start with using a recursion tree for factorial. Okay, let's start with that. And let's use this example here, factorial number 3. Let's use that one. Okay. So what I will do is, let's now see, we want to invoke factorial 3. So think about, I'm trying to compute factorial 3. In order to compute it, you want to think about whether this is more like a base case computation or it's like a recursive case computation. So look at 3 here. It's definitely not matching 0. So it must be a recursive calculation. It should be equal to the 3 multiply factorial 3 minus 1, right? So now for this one here, I can split it into, let me do the following. Sorry, let me just see where my eraser is. There we go. Okay. Yeah, sorry for the delay. So we start with factorial 3. 3 is not a base case. So by definition, it's going to be 3 multiply factorial 3 minus 1. 3 multiply factorial 3 minus 1, which would be 2. You can think about while we are calculating this one here, this here is kind of being suspended. We cannot really know what this is until we actually know what this is. So it's really keep being suspended until we reach the base case. But let's see how we get there. So factorial 2 over here, still not a base case. So we're going to split that into 2 times factorial 1. 1 here, still not a base case. We still have to split that into 1 multiply factorial 0. And you can see that finally, 0 over here is the base case. So once we reach the base case, we will be able to set the result to be 1 and return 1. So this is the case where we try to return and then go on. All right? So what's going to happen is, for this one here, it's going to return just 1. Right? And then we calculate this result. Remember, somehow factorial 1 was suspended because we wanted to calculate what factorial 0 is. But now that we know it's 1, 1 times 1 is going to be 1. So factorial number 1 is also going to be returning just 1. And then factorial 2 was suspended because we were waiting for factorial 1. Now that we know it's 1. So it's going to be 2 times 1, which will be 2. That one there is going to be 2. Finally, we try to calculate what's factorial 3. Now that we know factorial 2 is 2. 3 times 2 will be 6. So we know that here is going to be 6. So finally, this is the result to return. So this is the higher level. You don't really have to touch the stack. You just have to know whenever you have a method call, it might have to be split into multiple recursive calls. But in this case, just one recursive call. You may have to keep splitting until you reach the base case. From there, you're going to keep returning and keep computing. Okay? Any questions about this one here? Okay? Okay. So what I would do is I will try to trace the same thing using a stack. And let's see how that one's going to work. Okay? It's not going to take too long, but you can already kind of get some feel about if you want to trace using a stack some more complicated problem, especially Fibonacci, which we'll see in a moment. It's not very fun exercise, but it's very fundamental. You should know how to do it. Okay, let's do this one here first. Okay, let's start with, again, we want to compute factorial 3. So first of all, we're going to have this method call being active, put that into the stack. All right. So we are calling this method for the very first time. It's not recursive call, just a very initial call. So n here will just be 3. All right. And then we're going to check to see what 3 is. Apparently 3 is not equal to 0. So we don't go to the base case branch. So we're going to go to this branch over here. That one there, we're going to do 3 multiply the first recursive call. And the first recursive call is going to be factorial 3 minus 1, which will be 2. At the moment, you can think about we put factorial 2 onto the stack. So this guy here is active, and this one here is being suspended. All right, so far so good. Okay, let's now handle factorial 2. That one there, we're trying to call this method here for the second time. The input is now 2. All right, and then it's not base case. 2 is not equal to 0. I'm going to go for recursive case, which will boil down into 2 times factorial 2 times 1, which will be factorial 1. Okay, so to really compute factorial 1, I'm going to put that onto the stack. So at this point, this is active. All the others are being suspended. All right. Okay, we might need to get one more. Okay, let's now compute this one here. So we're going to go for 1 here. So it's going to be 1. So n value is going to be 1. So 1 is not equal to 0. So we're going to compute the recursive case for the third time. So it's going to be 1 multiply, and then factorial 1 minus 1, which will be 0. So we're going to push factorial 0 onto the stack, right? So now you can see 3 methods are being suspended, namely this, this, and this. And let's do a little bit of preview. As we reach the base case, we know that things will start returning. So that means it's time to really gradually terminate the recursion. Okay? So this will be first return, and then this will return. and then this will return. And finally, this will return, which is what we are trying to compute in the first place, gradually. Okay, let's see exactly how it's going to finish. So we're going to do this one here. So we execute the method here for the fourth time. So it's going to be value 0. This time, it is going to satisfy the base case. 0 equals 0, set the result to be 1, and then we return the result, which will be 1. Okay? So think about this one here is going to return 1. Okay? Just remember that one returns 1. So now what should we do? Think about what's on the top of the stack. It is factorial 1. Factorial 1 was here. It was suspended because we were waiting for the return value from factorial 0, which is right here. Right? So now we're going to replace that one there just by 1. Okay? So now for factorial 1, we're going to calculate 1 multiplied by 1, which would be 1. So set the result to be 1 and return 1. Okay? So this one here will be return 1. Okay, keep that in mind, is return value 1. And then the next method to handle will be factorial 2. It's now become active. Factorial 2 is this guy here, right? It was suspended because we were waiting for factorial 1. But now that factorial 1 has returned 1, we're going to replace that one there just by 1. Okay, and we compute 2 times 1 is going to be 2. So that means we're going to set the result to be 2 and then return 2. So we're going to return 2 from over here. All right? Okay, finally. So now the only thing left is factorial 3. Factorial 3 is right here. It was suspended because we were waiting for factorial 2. And that one has already returned 2. So replace that value there by its return value 2. So now when you compute the final one, 3 times 2 over here is going to give you 6. So that means this here is going to return 6. So that's the final return value. All right? So if you compare the last method call, return 6, and also at the top over here, 6. They are consistent. All right, any questions? Any part that's kind of not as clear? All right. I would say in the exam, you will be expected to do stack tracing for something slightly more complicated, slightly. But I'll give you exercise and give you solution. If you practice that, you should be okay, okay, for the exam. Okay. All right, guys, are you sure? No question, right? We're slightly ahead of yesterday by a few minutes. So, okay. So why don't we do just one thing, okay, very quickly, and then we can take a short break, okay? Or 2 things, to be more precise. So factorial is really the first example we want to learn about recursion. It's usually something very trivial. You might very rarely run into any simple problem like that in reality, just very simple. And to be honest with you, if I were to program factorial, I might just do it using a loop. I may not use a recursion. So, but in this 3 lecture here, we want to show you recursive thinking. So we are taking some problems, even though they might be able to be solved by using loops, but we still use a recursion, just to show to you, right? Just clarify that. Okay, let's see 2 common errors. First one, I can modify the factorial a little bit. Is this going to work?
No.
What are we missing? We're missing base case, agree? Okay. So let's see what's going to happen if you have this one here. If I start with factorial, let's say 3 over here, right? By definition, there's only one choice for me. I don't have a like if then else. It's going to be split into 3 times factorial 2. That one there split to 2 times factorial 1, split to 1 times factorial 0. So far, it's the same as the correct version. However, if you try to execute this one here, you still only got this branch to go, right? There's no like a if then else. So that one there is going to go for 0 times factorial minus 1, etc. All right? So you can keep going on and on and on. So we have something called infinite recursion. And in Java or in Eclipse, you're going to run into some runtime exception. It's called stack overflow exception. Okay? Maybe you have seen that before, maybe, if you somehow program recursion before. If no, that's something you might see if you ever try to practice. You're going to see something called stack overflow exception. Okay. So you can think about every time you're trying to make a method call, you're just putting something onto the stack. Because you're putting so many onto the stack indefinitely, the stack simply go overflow. That's where the exception name comes from. Okay, stack overflow. Okay. All right, how about this one here? What's wrong? I do have base case. I got base case here. I got recursive. Yeah, exactly, right? So here you can see, remember the principle we said? Whenever you're trying to make a recursive call, make sure the input is strictly smaller than the original one. But it's not the case right here. What's wrong with that, right? This one here, you will never reach the base case, actually. Let's start with, again, factorial 3. By definition, it's going to be 3 times factorial 3. Again, by definition, 3 times factorial 3, and so on. The 3 there is never decremented. You never get a chance to reach to 0. Okay? Again, it is infinite recursion. Okay, so just make sure at least your recursion has a healthy structure. Namely, you should have base case. So this one here is missing base case. And this one here is recursive call, not on strictly smaller input. Okay, so these are the 2 most important ones. Yeah?
I think the answer would be no, but would the compiler know that this is something that shouldn't be?
Very good question, right? So your fellow student question was, let's say if I get either common error number 1 or number 2, is Eclipse able to tell that I should compile? It's a logical error. We'll put it another way. Remember we said something called undecidable? Well, again, just a little bit of connection there. Having infinite recursion is more like a runtime behavior, which is something compiler cannot check. Right? So that means even though your recursion might compile, it doesn't guarantee you don't run into overflow exception. It's a very simple pattern, I agree. Yeah, I'm more talking about just general. I agree with you. You know, for example, sometimes if you forgot to initialize your variable, you might get null pointer exception, right? They might figure out some easy pattern, but not in general. Yeah. Okay, awesome. Okay, why don't we take a short break and then we'll continue. Okay. Right, so second example is also a very typical hello world example to recursion. So it is a so-called Fibonacci numbers. So we are seeing a sequence of numbers over here. The sequence is an infinite sequence, so you can go indefinitely. Okay, so you can think about it's more like an array of integer. But here the indices of the array will start with 1, not 0. Okay, so you can think about you got indices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. You can go towards infinity. Think about it's more like infinitely long array of numbers. Okay. So I'm just going to tell you the solution right away. Right. It's a very common, it's a very famous pattern, you know, about computation. So by definition, the first 2 numbers in the Fibonacci sequence are always just 1. So you can think about the first number here is called the first number in the sequence. So F here is a Fibonacci sequence, right? We'll put a subscript 1. And the second number here is F at index 2. Okay? And then, so you can see starting from index number 3, okay? Starting from index number 3 and onwards, okay? So the definition for that particular element is, if I want to get what is this, it's going to be the sum of the previous 2 numbers, 1 plus 1. If I want to get Fibonacci 8, I should really get 6 and 7. 8 plus 13, which would be 21. If I want to get 11, it's going to be 9 plus 10. Right? The pattern just go on. Okay? So that's the definition. All right? But of course, you can verify. Okay? And I want to show you something that's interesting. Okay? Let's take a look at Fibonacci 4. Let's start with Fibonacci 4. By definition, it is Fibonacci 2, Fibonacci 3. Right? Fibonacci 2 over here is going to be just 1. Thank you. Just base case. Right? Just 1. Fibonacci 3 over here is actually going to be Fibonacci 2 and also Fibonacci, what am I doing? Fibonacci 1, Fibonacci 2. Okay, okay with that? Okay. 1 and 2, right?
1 and 1 is 2.
Of course, it's just 1 and 1. Okay, good. So let me just do one more. Okay, you will see that the structure itself is going to be repeated. So let me just do one more, and you will see what I mean. So here, if I try Fibonacci 5, by definition, it's going to be F3 and also F4. Right? Agree? So now, you can see that in order to compute F5, somehow the computation of F4 already contains its result somehow. Right? Because this F4 over here just corresponds to the top right here. So what I can do is I can simply just copy this particular structure and then just paste it right here. F4. F3 the same thing, yes. And over here, you can see that this one here, if I copy that, it's just going to be right here. Yeah. It's a bit messy, but you see what I mean, right? I'm just saying the tree itself can somehow be shared. Somehow the structure will just repeat itself, okay? You kind of see my point. Okay? But this is something we will explore a little bit later in the more advanced like algorithm course to see how Fibonacci sequence itself to compute it is actually very inefficient. But for this course, we just see how we can do the recursive definition. Okay? Okay, let me put this aside. Okay? This one here just to show to you some observation. Okay, I'll put it aside. So now let's take a look at the recursive definition. Okay? So in this case, we got to talk about base cases. So Fibonacci n will be, so we got 2 base cases. It will be 1 if n is equal to 1. 1 if n is equal to 2. Right? We'll talk about these 2. Okay? So we got 2 base cases. So these are the 2 base cases. Recursive case will be if we pick any arbitrary n here, it's going to be n minus 2 and also n minus 1. Okay, add them up together. So it's going to be if n is strictly larger than 2. In that case, we got f n minus 1 plus f n minus 2. So we're basically making 2 recursive calls. You can think about this one here and this one here. We're basically calling Fibonacci itself. To calculate Fibonacci for n, we're going to call Fibonacci n minus 1 and also call Fibonacci n minus 2. So we're making 2 recursive calls. All right, so that's a point I'd like to make. So we got 2 recursive calls. Questions? Yeah.
In the base case, why do you only use 1 and not 0?
Oh, it's definition. So Fibonacci sequence is named after some mathematician with last name Fibonacci. So when they invented the sequence over here, they just started sequence with 1 and 1, and then so on.
Oh, so is the first one like 1 plus, is it just starting at 1?
Start at 1, yes. The first 2 elements are always 1, yes. So, of course, if you invented your own sequence over there, of course, it can be defined differently. But for the Fibonacci, it's always going to be 1 and 1, and then so on. Okay. All right. So now I would like to say 2 things about Fibonacci. Okay. Number 1, this will be some Java implementation. If you look at the lecture site, all the example I talk about in class is already in the lecture site, the Java code. You can play with it in the Eclipse. So let's take a quick look. So you can see n equals 1, 1, 1. N equals 2, 1, 1. Recursive case will be the else part. You can see Fibonacci n minus 1, Fibonacci n minus 2. Right? Again, you can see the one-to-one correspondence. Okay? So now the exercise for you to try is to see how you can use a call stack to trace Fibonacci of 4. Okay? As you can see, Fibonacci 4 will correspond to just this number. Very small number to compute. However, to trace this one here using a call stack precisely is more complicated than you might think. Right? So that's the exercise I would like you to try. All right? I'll keep this page clean over here for you to try. And then once you're done, the solution can be found over here. It's more like a solution walkthrough. So if you want to walk through the solution with me about this one here, you can also do that. Okay? I'll show you where you can find it. You can just go to the lecture site. And then you'll see under exercises, tracing Fibonacci 4. All right, that's exactly the solution you can go through. But if you feel confident enough just by using the stack yourself to trace it, no problem. You don't need to look at the video, but it's there, okay, if you want to look at that. On the slides, you also see some written trace about Fibonacci 5. You can take a look at that one as well. It's just another example, okay? I would say so far, the recursion that we have been seeing is just like a recursion on numbers. We haven't really seen any recursion on some structure, like a string or maybe array. That's something we'd like to start looking at. Okay. Any questions so far? Factorial, Fibonacci, we okay? Okay, good. So if you go back to the slides, so we are now done with factorial and the 2 common errors and some tracing for factorial. And also we got Fibonacci sequence, we just spoke about it, the Java code. And also this is something I also did on the slide, this is Fibonacci 5. But for you to really trace using a stack, just do Fibonacci 4. That should be enough for you to get an idea. Okay. All right, that one you can also take a look. Okay. And let's now start talking about recursion on some structure. So for today, I want to just talk about some useful library methods that you may use in the exam. Okay, so in the exam, if we ever ask you to do recursion on a string, you will be restricted to really use its empty substring and also character add. So these are the main 3 methods. That'll be sufficient for you to use, really. Okay, so we're going to talk about how to use them very quickly, and then we'll just do one example for recursion on string. So I think after today, you're already ready to really go to that coding batch site. Go to recursion number 1. Try something there. Okay, I'm pretty sure you can do something already. You know, if you're struggling, using ChatGPT is not a bad thing at this stage because you're learning. Using AI to help you learn is a good idea. I wouldn't discourage you to do that. I would encourage you to do that, actually. All right, so let's now go over the methods that you will find useful. Okay, let's take a look. Okay. So let's now start with some visualization. Okay, so let's say we got one string, A, B, C, D. Okay, so the best way for you to visualize it would be like an array of characters. So if you think about S over here, it's pointing to an array of how many characters do we have? We got A, B, C, D, so 4. So we got 0, 1, 2, and 3. 0, 1, 2, and 3. So we got A, B, C, D. A, B, C, and D. I believe in programming language C, maybe you're taking 2032 or 2031, or you know C already. I think the way they treat a string is also like an array, like a sequence of characters. They also got some null character at the end to signal the termination of the string. But it's not the case for Java, right? The way you visualize it is simply what character you can see in the string, that's it, in the string. Okay? You don't have to worry about anything about null character, just in case you're confused. So we look at A, B, C, D here. You can also try to put the indices, 0, 1, 2, and 3. Okay? That's how you visualize it. And very simple method, you can see how you can check to see whether or not the string is empty. Does it contain 0 character, right? Apparently, this string over here contains more than 0 characters, so that should be false, right? Simple, okay? Sometimes, whether or not the string is empty could be one base case for you, okay? Because you can think about whenever we are calling recursion on string, you can try to call the recursion on the basis of the length of the string. Could be length 0, length 1 could be the base case. And then any length larger than 1 can be the recursive case. That's one common pattern. But we'll see later. Let's now discuss this interesting method called substring. Okay. Substring over here. Substring. Also substring. Also substring. And also substring. Okay, the substring method is going to be invoked on some string objects, and that one there is going to return another string. But we want to know what exactly it is going to return. Okay, let's now talk about its definition. So when you say any string s dot substring, and you will need to pass 2 characters. Sorry, not 2 characters, I beg your pardon, 2 integers, I and j, numerical values, I and j. And there's usually some implicit assumption over here, okay? So the assumption is I should be less than or equal to j. I'll explain that. It's actually an important assumption, otherwise there will be some calculation that might go wrong. Okay, I'll get there, okay? Just make that assumption. So all the example I gave to you, 0, 0, 0, 4, 1, 3, 0, 2, 2, 4, is the case that the first argument less than or equal to the second arguments. Okay, that's the assumption. And now what does it do? It's going to return a string. It's going to return a string including characters from a range of indices. All right, over here, we specify I and j, but it doesn't mean you're going to go from index I to index j, not really. Okay, this is the part you want to be careful. It's going to go from I to j minus 1. Okay, I to j minus 1. All right. And I'm pretty sure maybe back in your calculus class, you learned about open versus closed intervals. Right? Okay, let's now revisit that very quickly. Very simple stuff. Okay, very quickly. So if you remember, let's say here, if I got maybe 1, 3. So that's really about 1, 2, and 3. So the square brackets tells you that both ends are inclusive. On the other hand, if I got, for example, 1 here and also 3 here, but parentheses, that means the right-hand side is open. It's not going to include 3. So this will be actually 1 and 2. All right? Simple stuff. So in substring over here, when I say I and j, so there are 2 ways to understand this. It's going to include all the characters. You can think about including I all the way excluding j, or including I all the way to including j minus 1. So these 2 are equivalent. Okay? All right. Let's now do a quick example. Okay? Just keep that in mind. I will leave this guy here to the last. All right? This one here is going to be from index 0 to index 3, which is going to be 0, 1, 2, 3, the whole string, A, B, C, D. All right? And here, if I got 1, 3, it's going to be from indices from 1 to 3 minus 1, which will be 2. Right? So that will be 1 and 2, which will be B and C. So that will be just BC. And what about this one here? Can you try to compute it? What's going to happen here? So I'm trying to concatenate 2 substrings together. Mm-hmm. Anybody?
Which is AC? 0 to 1, 2 to 3, so ABC.
Okay, everyone can see that? So here you can see that this substring is going to give you characters from indices 0 and 1, excluding 2. And this one here is going to give you 2 and 3, excluding 4. Right? So 0, 1, 2, 3. So still the whole array, this whole string, 0, 1, 2, 3. Okay? What about here? Okay? So this one here, we're going to look at some little formula here. You want to think about whenever we say we got our interval here, let's say 1, 3. You want to ask about what's the size of this interval. Okay? The size of the interval here, right? You can see simply just 3. Okay? And then I can give you another one. Let's say if I got maybe from 0 all the way to 10, for example, this will be 11, right? Size 11. So there is a formula. Okay, I wouldn't go into deriving it, but it's a simple formula you can think about for the size of the interval. So if I got interval A and B, and of course the assumption is A is less than or equal to B. A is less than or equal to B. And the size of this will be B minus A plus 1. All right, that's the formula. Okay, if you plug it in, 3 minus 1 plus 1, 3. 10 minus 0 plus 1, 11. All right, the same formula. Okay. So now, if you go back to here, for this one here, all right, when we got 0, 0, it would be as if we try to calculate 0 and then minus 1 inclusive. So now, what will be the size for this interval? Minus 1 minus 0 plus 1, which will give you exactly 0. So that means this one here is going to give you some 0 interval of indices to be included. So that will be empty string. Okay, right here. All right, question about this. Go ahead.
How does this empty function deal with like a string with only spaces?
Only spaces. Oh, good. Each white space is also considered one character, right? So for example, good question. So for example, if you got, let's say it's empty. Let's say I got maybe empty space, empty space, empty space. It will still be false. Because as long as it's not empty string containing no characters, it should be false. Okay? Good.
So you can think of it as dot equals the empty string.
Equals?
You can think of like dot equals the empty string.
Yeah, you can think of that too. Yes, yes, indeed.
So if A is greater than B, it's just going to be a runtime error.
So say it again.
A is greater than B, it's going to be a runtime error.
It's not going to be runtime error. If you say A greater than B, you can give it a try. So for example, if you say from 3 to 2, my guess is substring, right? If you say substring 3 and 2, in which case we're kind of breaking that assumption about 2 less than or equal to 3. I believe either it's going to give you some exception or it's going to be empty. Either way, I can give it a try. Okay, that one I'm not exactly sure. We may need to try it out. Empty or exception. But for sure, it's not going to give you any substring. That's for sure, right? Mm-hmm. Question.
So you mentioned the empty string. What does the empty string look like in Java?
Turns out-
Is it just a null pointer?
Index out of bound exception.
Exception. What kind of exception was that?
Index out of bound exception.
Okay, sure. So you mean the, say it again, sorry.
So you mentioned the empty string.
Empty string, yes.
Yeah, in Java, is it like a null pointer or is it like a specific character?
You can think about empty string, right? Okay. For empty string. So let's say, for example, let's say S is empty. You can think about S is pointing to some string objects. And the string itself may have some value array. And that array is supposed to store characters. But that array right now is simply just an empty array. There is some reference there, it's not null, but just that the length of the array is just empty, just 0. Yeah. Good. Yeah, so just back to your fellow students' discovery. It's going to be index out of bound exception, you said? Index out of bound exception. Yeah, good information. Good. Good. All right. Let's now just do one problem on recursion on string. Just one. Okay. It's an interesting one. Again, every time you want to talk about recursion on string, this will be the hello world example. People like to talk about this one first. It's kind of a fun one. I kind of like that. Okay. So it's something called palindrome. Do you guys know what a palindrome is? Okay. Basically, it's a string. If you read it forward and backward, you read the same. Okay. Let's see. Okay, so let's talk about simple string, like a easy string, like a very small string. Is empty string a palindrome? Yes? If you read an empty string forward, backward, just empty string. So it is a palindrome. If you got a single character string, yeah, A, backward, forward, okay. Do you know about any palindrome yourself? Oh, everybody knows about race car. Yeah, that's good. Yeah. Everybody, yeah. Okay, good. Yeah, madam is one. Okay, it's a palindrome. Okay. And also race car. Okay. And man, not palindrome. Okay, M-A-N versus N-A-M. Good, good, good. Okay, you guys get the idea. We only do this one today. Okay. Let's now just talk about how to think about the problem recursively, and then we are done. Okay, I want to just be in sync with your fellow student in section B. Okay, let's talk about it. Okay. So we talk about, let's say, race car and another string. I made it up, and these three. Okay. So how can we think about solving whether or not a string either true or false? True if there's a palindrome. False if it is not a palindrome. Think about you're trying to read it forward and backward at the same time. That's what you want to think about, right? When I try to read this string over here forward, I'm going to see this character first. When I try to read this string backward, I'm going to see this character first. First of all, we agree? That's a very important insight. Okay? So one way to think about it is I try to look at the first character here and then also the last character over here. In this case, they are the same. In general, am I guaranteed if the string has the same first and last character, it's going to be a palindrome? Not necessarily. You still have to go into the middle except for the first and last character, right? So that means you still actually have to go on to this middle part over here. Okay? It's a very important insight. I'll write it out. Okay? So here, the first and last characters the same. So that means there is a chance the substring. And you can think about, we're going to see the Java solution on Thursday, but you can think about in order for me to get the substring from the second character to the second last character, what kind of indices should I specify? Something like that. You can think about it, right? We'll get there on Thursday. The substring minus first and last character is a palindrome. Okay, it's a very important insight. On the other hand, you can see that the first character here is A, the last character here is S. Reading forward, I see this first. Reading backwards, I see that first. Now they are not the same. For sure, I can say false right away, right? Because there's no way it can be a palindrome. They already read different. Okay? So given that these two are already different, false. All right, let's do one more. Okay, so you can see R and R. For that, we look at the middle part. For the middle part, we try to look at the A and also A. They are also the same. In which case, we try to look at this, the middle part, which will be CE. AC. And for that, we look at C and C, which is the same. But now, finally, we look at the EA part. right, the middle, right? So now for EA, you can see this one here, no way, it's not a palindrome. In which case, the method should really somehow recursively return false, okay? So try to think about this kind of intuition. This will be the kind of sketch you want to do on the paper before you even try to program the method. Okay, think about this inside here, and then we'll see the Java code. We'll do some quick tracing, and then we'll do the other two quickly on Thursday. All right, we'll finish earlier today. Okay, thank you. I'll see you on Thursday.